right, in 2010. From 2010, she was a research fellow, and then she started to work in the industry, working mainly as a Scala developer, a Scala software engineer, and she really worked with systems that need to handle millions of active users. So she's a real expert in distributed systems, and today she would like to present some her experience about distributed systems, how to solve problems occurring in distributed systems. So Maria, please.
So good morning, everyone. First of all, I would like to thank you, Melinda and Scott, and the Erlangen team of the workshop to invite me for this presentation. It's a real pleasure to be with you all here. So, as Melinda said, actually this is not really recording.
Sorry, maybe we have to just.
So maybe if we adjust that to be 100%.
The page. No, unfortunately not. Sorry, we haven't tried it before.
Screen resolution different.
Yeah. Which one you suggest? I think that should be
1024.
Okay.
Cool. So, yes, as I said before, Melinda said, my name is Maria Rubio, and I'm here to speak about how to solve some distributed systems problems by using actors and the Akka library, the Akka toolkit. So, first of all, like a few words about myself after Melinda's introduction. So, I studied computer science in the University of Murcia, and then I moved to London where I studied my master's. And I started working in the industry, so I've mainly been a consultant doing some Java, but then 3 years ago I started working within the tax platform for the United Kingdom. And in there I moved to use microservices as well as Scala, and from there onwards I started working as a Scala dev, which was a bit more than 3 years ago. Then I was working as well for a year building the Greenfield project related to the newsfeed at Shazam. And then recently I'm working as an associate of Equal Experts, where I'm allocating as a consultant for a major UK investment bank. So before moving forward, the first thing I would like to say is to give my apologies about the lack of my drawing skills. So from there you could notice why I build software for living and I'm not an artist. So let's start with the contents. So first of all, I would like to give like a brief introduction about Monolith and microservices architectures. So when speaking about microservices, it's also a good thing to explain a bit how Monolith architectures are and compare them with microservices. Then I'll give an introduction to the Akka toolkit, and from that point on, what I'm going to do is to present a use case where we are all going to build card payments fraud detector, a very simple one which I've called Fraudy, and in there we are going to go through how to do that using actors in Akka. Then I will show you like a few cases of how to use Akka persistence, Akka clustering, and then a brief description of a use case where we'll be able to use Akka strings, and then some conclusions. So let's start with that. So when I try to speak about microservices, there is a very good online resource which is from Martin Fowler's website where he speaks about microservices. I'm sure some of you have seen it already, but if you haven't read that, I would totally recommend to read about it. So in here I've just copied the definitions that Martin Fowler is giving about monolith and microservice architectures. So a monolith architecture consists of developing an application as a single unit, And on the contrary, a microservice architecture consists on developing an application as a suite of small services, and each service is running its own process and is communicating with some lightweight mechanism such as REST API. So in here, no more words. I would like to show you here, like I introduced to you the Monolith monster. So I usually refer to him as a monster because sometimes monolith applications are quite scary and difficult to manage. And on the contrary, we've got there the microservices, which are like very small monsters there, which are much easier to manage. So let's have a look at some comparison about it. So when you need to deploy a monolith application, usually it's quite difficult because, well, it's not difficult. You need to basically build and deploy absolutely everything. And as an opposite with microservices, what you need to do is to just build and deploy like one of these single monsters. Then when we need to scale a monolith application, the way of doing it is to replicate the whole application across different servers, and this is how you scale it. However, for microservices, this thing is different because you only need to replicate like small pieces of your whole architecture, which is going to be the microservice. And from there you can see that there is one advantage, which is that you are going to save a lot of server resources, which are often expensive because you will need to rebuild and deploy the whole application, and you will need less memory, for example. And also, for example, if you want at some point to retire a microservice, it will be as easy as stopping the microservice, not running that in production, and that should be enough. In the monolith architecture, this thing will be impossible to do. Then usually when people are working in monolith architectures, they tend to have like different teams of specialists. So for example, you will have like the database engineers, you will have backend, front-end engineers, and so on. And they all work in isolation in a product, and they will need to coordinate to deliver something. However, in microservices, actually, this is like more smooth, and then you are able to merge all these specialists together to create a team which is going to be in charge of the product. And this approach actually is going to empower users a lot because they will feel responsible for the product they are building, and they will be able to deploy and maintain it. So then, the number of choices. So when you are working in a monolith application, usually it's the choices are limited about the technologies and frameworks and programming languages that you can use. Imagine that you start with a Java monolith, so from there the number of frameworks you can use is limited. However, if you use microservices, there is nothing which is going to stop you to use different languages or frameworks in each microservice. So for example, if we need to create a real-time communication system, then we can use Erlang in one microservice, and then if we need to add some advanced image processing, we can use C++. So there is nothing stopping us to do that. And yes, finally, about the data management, monolith architecture is usually connecting to a single database. And for the microservices architecture, we tend to basically split the database in business areas, and each microservice will handle a small piece of the database, which is related to the business logic of the microservice. So after the previous slide, you may think here that I'm here to sell microservices to all of you. So actually the microservices are not perfect at all, and there are some drawbacks that I would like to explain in this slide. So the first drawback, and I think is quite straightforward to see from how microservices communicate, is the speed. So as you know, we've got different microservices. Usually they are connected using a REST API, and the remote calls are pretty slow. So this is like the first problem we see. Then the second problem is related to the design, because with microservices, and I've been working with them for almost 4 years now, I've usually seen that people tend to overdo them. So for giving you an example, and it's a personal example, I was working in a project where we had like a 3 months discovery phase, where we were basically trying to solve some problems that we were going to face later on in our project. So during this 3-month phase, we decided to start with microservices. And then we spent quite a lot of this time trying to actually communicate between the microservices, deploy them because you've got like several microservices you need to deploy, so this thing takes time. And then, even though this thing was helping us to find out like some problems with the architecture we designed, it didn't allow us to explore some other options that we should have explored within these 3 months to find out more important problems or explore like some third API systems that we could use. So my recommendation about designing microservices is to basically start with a monolith, and as soon as you see the big monster, try to split it. And transactions is always the hard part with microservices because managing transactions in a distributed system is usually very complicated. So the way of managing transactions with microservices is usually trying to isolate the transactions in one single microservice, which is going to be responsible of managing the consistency there. And then finally, failure, which is my favorite topic here. So usually when you have microservices, the failures you see there are a lot of more cases about failure. So if you have a monolith, you will have like, in the Java world, for example, you will see some exceptions, you will be able to catch the exceptions and that's it. In microservices, there are a lot of more things that could go wrong. So for example, I don't know, a server is not responding or, yeah, so in this case, you need to basically follow some patterns to fix the failure, and then actually we are gonna see how to deal with failure and actors in distributed systems later on. Cool. So now that I've spoken about microservices, let's give a quick introduction to Akka. So Akka is a toolkit for constructing concurrent and distributed applications using the Java virtual machine. And then it's an actor-based concurrency model, which is inspired from the Erlang actor model. And there are 2 supported languages there, which are Scala and Java. I've only used, to be honest, Akka in Scala, but the library, the Java library, has evolved quite a lot and it's also ready to be used in Java. And about Akka, there are like 4 main features. So the first feature is Actor, which is a high-level abstraction for distribution, concurrency, and parallelism. They communicate with a message-driven model. In here, in Akka, you can actually deploy several millions of actors within one single machine. Then also Akka is fault tolerance, which is based on the let it crash principle, meaning that if an actor dies, that's okay. We can always recover from there by using the supervision strategy. So the default supervision strategy in Akka is when an actor dies, Akka will restart it automatically. However, you can customize this supervision strategy by using the parent who created the actor, and then from there you can actually specify what to do with an actor that has crashed. Like for example, stop the actor, resume or restart the actor. Then one of the main features that we are going to have a look at during this presentation is the location transparency of actors in Akka. So Akka is designed to make the actors to be running in a distributed systems and to be transparent to the end user of the toolkit. So we are going to have a look at an example of Akka clustering at the end of this presentation. And also the last thing is Akka persistence, which is allowing you to restart the state of an actor when the actor crashes. And we will see like some features of Akka persistence later on. So from now on, we are going to try to build a very simple card payments fraud detector, which I've called Fraudy here. And the high-level requirement for that is expressed here as an acceptance criteria, which is saying that given an active bank card, when the total value of the payments exceeds the $3,000 within 1 hour since the first payment, then an email is sent to the card owner to notify about the suspicious transactions. So, first of all, I would like to introduce here the fraud detector actor. So this actor we will have one instance of this actor for each card number we have. So for example, if this actor is processing the payments coming from my credit card, then we will have one actor allocated to my credit card number. Then this actor has a notebook, and I will refer during this presentation to this notebook as the internal state of the actor. So let's have a look at an example. Let's imagine that I'm spending $100 with my credit card, so the actor receives the payment, and then the actor is gonna keep track of this first payment in his internal state. So I will do another payment of $1,800 here, and then the actor again will receive the payment, and it will update his state. And then the actor will notice that I've exceeded the fraud threshold amount, which was $3,000, and then the actor will send a message. So far everything is very simple, but let's have a look at how to do that using Akka. So these examples are using Scala. Yes, I think it should be all right. So let's have a look. So first of all, this is my fraud detector actor. So you can see here that we've created an actor in 40 lines of code. So the first thing is, this is a class which is going to receive two params. The fraud threshold, in our case it will be $3,000, and then we will have like a reference to another actor, which is going to be the fraud notifier actor, and this actor will be in charge of deciding what to do to notify about fraud. And then you can see that for implementing an actor in Akka, we only need to extend the actor class from the Akka library. And by extending this class, there is something that we will need to do, which is to implement the receive function. So this receive function is going to be the function receiving all the messages coming to the actor and then deciding what to do. So in this particular case, this message from the outside, this actor from the outside world will receive payments. So which is that line there. So you can see that when the actor, as we saw in the example, when the actor receives a payment, we are increasing the money spent state inside the actor, and then we will check if the money spent is over the fraud threshold. In this case, it's not, so we will continue. And in here, what we want to check is if the first payment for the actor is, if this is the first payment for the actor. So in case that this is the first payment for the actor, because the requirements were saying that we will notify fraud within a window of 1 hour from the first payment, what we are doing here is to schedule a timeout message, which is basically gives you like a scheduler inside the actor system where you can say, I want you to schedule a time is up message in 1 hour and send it to myself. So what this thing is going to do is to send after 1 hour one message to the actor to say, okay, the time is up. However, in here, if we go to the use case that I presented before, where the first payment was received, the actor was updating the state, and the second payment was received within 1 hour, then the actor will come here, and then it will determine that I've spent more than $3,000 in less than 1 hour, and then the actor will actually send a message by using this exclamation mark symbol there to the fraud notifier actor, and then it will move to the next state. So in this particular case, when the actor is in this state, it's because the fraud has been detected and is waiting for the fraud notifier to reply back and say that the fraud has been notified. So once this thing is happening, then the actor will suicide by stopping himself. So far you can see that, yes, we've built the actor in a few lines of code, but this actor is not very resilient. So how do we handle the failures here? What happens if this actor crashes after processing the first payment, and then we lose the state for the first payment? And this is actually where Akka persistence comes to the rescue, which is going to allow us to keep the state of the actor and restore it after the actor is restarted. So let's have a look at an example here. So first of all, for making our previous actor a persistent actor, instead of extending the actor class in Akka, what we will need to do is to extend the persistent actor, and then after that we will need to implement 3 functions, so which I'm going to explain how to do it now. So the first one will be the persistence ID, the second one the receive recover, and the third one the receive command. So let's have a look at the persistence ID there. So in this particular case, the persistence ID is a function which is defining the ID that we are going to use to persist the events into the event log of the actor. So in this case, it's quite straightforward to see that the persistence ID for this actor is going to be the car number, which is going to be unique, since we will have one instance of the actor for each car number. So the second thing here is the receive command function. So as you can see here, this code is quite similar to the one we saw when we implemented the first iteration of the actor, where the receive function is exactly the same, almost the same, but instead of being called receive, it's called receive command. And then here there are like 3 different lines, which are these lines where we are using the persist invocations. So the first thing we will do here is once these persist functions are going to save events into the events, entries into the event log that we will have. So I've forgotten to mention before that Akka persistence can have a local or a distributed events log. And then there are out there a lot of plugins available to use different types of events logs, such as Cassandra, MongoDB, DynamoDB, and much more. So if you want to check the ones available, you can visit the Akka website. In here, well, we will come back. So we've got the persist function, which is going to make sure that we save an event into the events log. So in this particular case, this function is asynchronous, meaning that until this event is persisted into the events log, the actor will not continue executing this. So this is going to guarantee that we are able to reveal the state of the actor once the actor dies in the middle of processing something. So I would like to mention as well that Akka is coming with a persist async function, which is going to do the persistence of the events log asynchronously, and this is quite useful when you have some relaxed consistency requirements, and then you need to have a high throughput through the actor. So let's have a look at the previous example. Let's imagine that after the first payment, my actor dies. So what happens here is we will go here the first time, process the payments, and then we will persist the payment event with the amount and the time where the payment was done into the event log. And then our actor will continue here, and then at some point it will crash here before receiving the next function. So what happens there is that what we need to do is to recover from this situation, and this is going to be done by using the receive recover function, which is the last function we had to implement by extending the persistent actor class. So for doing that, actually this function is going to receive all the events which were saved in some specific order, and these events are going to be played and recovered, and then at the end, when the event log doesn't contain any more events, then we will receive a recovery completed message. So in the previous scenario where the first payment, when after processing the first payment something went wrong, what we will do here is to say, okay, when we receive a payment event, we are going to increase the amount spent, and then if the first payment is empty, which it is because it's the first event we are processing from the log, then what we are going to do is to introduce the updated state with the first payment. So once we only had one event in the log, which is like a very simple use here, but after that we will receive the recovery completed message, where we will see that the money spent is not greater than the fraud threshold, so we will move here, and then what we are going to do is to basically schedule the timeout message in 1 hour, but in this case we will need to do some time calculations to make sure that it's from the time of the message, when the time of the payment was received. And then the actor will move to the receive command receive function, and then from there it will continue processing new messages. So if my second payment of $1,800 arrives, then the actor will have the state correctly initialized after it's restarted. So having said that, now it's time to see how we are going to scale the system. So in this particular case, right now it's quite unlikely that we will be able to run all the actors in one machine if we need to detect the fraud for a huge bank, for example, for all the payments from a bank. And also, obviously, for the fault tolerance, we don't want to have all the instances of the actor in one machine. So that's why ideally we would like to distribute all the actor instances across different nodes and then make it transparent to us or very easily to manage. So we don't need to worry about when a node dies and then we need to rebalance all the actors, or how to distribute the actors across all the different nodes and so on. So for doing that, this is where we will use Akka clustering. So Akka clustering again is a library inside the Akka toolkit, which is actually providing a cluster system which is going to do failure detection and is going to manage the distributed actors for yourself, and is actually using the Coshed protocol to communicate. So if you want to know about how the Akka cluster is implemented, on how the protocols are working, I would strongly recommend to go to the Akka website. It's a really interesting resource. So in this presentation, I'm going to cover only one very little part of Akka cluster, which is going to be Akka sharding, where we will be able to shard the instances of the actors we have across a distributed system. So let's have a look at an example. In here we've got a cluster which has two nodes, the red node and the blue node. So each of these nodes will have a sharding region there, which is going to be the one receiving all the payments. And then only one node in the cluster, which is usually the oldest node in the cluster, will have the shard coordinator, which knows where the other shards are. So let's imagine that the first payment from my credit card arrives to the sharding region. And then the sharding region, using some functions that I will cover later on, will decide that this actor needs to live in shard blue. So, but then the red node doesn't know where the shard region blue is. So the first thing that it will do is to go to the shard coordinator and tell the coordinator, okay, where is blue? Where is node blue? And then the coordinator will tell, okay, this is the actor ref to call node blue. So then our red node will create the actor, the fraud detector actor for my credit card in node blue, and then it will forward the payment to that actor. So when another payment arrives, because the red node already knows where it applies the sharding algorithm, and then it decides that, again, this payment for my credit card number goes to node blue, then it will automatically redirect the payment to node blue. So let's have a look at how to do it like very easily. So this is like a very simple example where we will see how we can configure Akka clustering. So the first thing I will move here, and this is the first thing we will have a look, which is the cluster sharding.start function. So what this thing is going to do is to create your shard region that we saw in the previous slides. So by doing that, this one is going to give you a reference to the actor that you can invoke and send all the payment messages through this shard region. So when the payments arrive to our system, we will send all the messages here. And then we will specify the type name of the actor we want to instantiate. These entity props are basically the properties for creating the actor, the ones that you saw in the first line of the actor, where we were sending the fraud threshold and the fraud notifier actor. And then also you need to specify the class that you want to instantiate. Then you will have some settings that I will cover after explaining these two functions, which are the struct entity ID and the struct shard ID. So these two functions are the most important functions you need to define here. So the struct entity function is going to extract the entity ID from each message which is going to arrive to the shard region. So in our case, every time a payment arrives to the region, what we want to do is to extract this entity ID. And in our case, it's quite easy because it will be the card number. So we are going to use the card number as the entity ID. And then the shard region will use this entity ID for creating the actor, and it will allocate this entity ID as the name of the actor. And then the second thing we need to implement is to decide where we want to create our actor. So in here, what we want to do is to implement the struct shards ID function, which is, again, in the same format as before. When we receive a payment, then what we want to do is to decide in the shard that we want to run the actor, and in this case what we are going to do is the hash code of the card number, and then with the modulus of the number of shards, and then that one will decide where the actor will be allocated. So you can see here that it's quite easy to configure, and there is one more thing that we will need to do in our persistent actor, in there where the card number, instead of coming as a param, will come now defined through the path name of the actor, which is using the entity ID result of the function that we saw before. I have to say here as well that Akka sharding has a flag that you can configure in these cluster sharding settings to specify that you want the cluster to remember the entities, meaning that if one of the nodes dies, Akka sharding should be able to take all the actors that were living in this node and then move them around the other available nodes. So this is, like, as you can see, for me it's fantastic because it's actually heavy lifting a lot of the errors and code that we need to cope with in this particular scenario. It will do it automatically for us by keeping track of the actors living in its node, and when the node is unreachable, it will move them. So this is, we are almost there. So this is the last part of the presentation where I would like to cover like a very high-level case where we are going to try to send notifications when the fraud is detected. And here there is no more code, so the previous slide was the last slide containing some code. But yeah, in here for sending notifications, I'm gonna show how to use, I'm gonna give like some example of how to use Akka streams for that. So let's have a look at, let's imagine that this is the architecture of our system where all the payments will come through a queue, then our fraud detector system will consume from this queue, and then when the fraud is identified, then it will put some messages into this fraudulent card payments queue. So once this thing is done, then we will have here a microservice, which is going to be the fraud processor microservice, which is going to consume from this queue and then send some emails to the end user. So for example, if I spend more than $3,000, then I will receive an email from this system through the email microservice to tell me, Maria, there is some potential fraud that we have identified. Please take some actions there. So in here, we may have the situation where the email microservice is pretty slow. For example, let's imagine that we are using a third-party API which only has a quota of 1,000 email messages sent per minute. So in this particular case, actually, what happens here is that if we've got like a lot of fraudulent payments coming through the queue, then our fraud processor will start consuming them as fast as it can, and then actually it will start sending all the emails. And then we will reach the quota. So how do we recover from this case? So obviously the email microservice will start failing, telling us, okay, I cannot cope with the load that you are sending to me, so what should I do? So then the fraud processor could do one thing, which is automatically resend the request that failed to the email server. But you can think from this specific case that this is a stupid thing to do, because what happens here is if the email microservice cannot cope with the load that you are sending, the thing that you want to do is to give the email microservice some time to recover. So in this case, what we could do is to implement here some delay using the exponential backoff strategy, which is going to send the messages after the fail after a short period. If it fails again, it will wait a bit longer, and then resend the messages, and so on, until the email microservice is able to send all the emails that we've got. But in here, the problem comes in the fraud processor. So if the email microservice is taking a long time to recover, we will consume, the fraud processor will try to consume as fast as it can from the fraudulent card payments, and then in this case the fraud processor will start buffering all the messages in memory, and then we will have here like a problem with which is going, this microservice is gonna die with an out of memory error because all the messages will be buffered in the memory of the system. So for coping with this situation, this is where we will use Akka streams, where we will define our source of data here. The email microservice will be the sink of data, where the data will die. And then in here, the flow processor will be like a step which is going to connect the source with the sink. And in Akka streams, you call this one as flow, basically. So in this particular case, what Akka streams is going to do is, as soon as it detects that the email server cannot consume the messages fast enough, then it will propagate some back pressure signals up to the source, and then it will mean that it will slow down the consumption of the queue. So we will fix the out-of-memory repair problem happening in the flow processor. That's it from me today. So as you can see, like working with microservices and distributed systems have a lot of advantages, but they are quite hard to manage and implement. And this is why the Akka toolkit is there to help us to solve some of these problems. So through my professional experience, I've used Akka quite a lot, mainly at Shazam, and for us it was quite easy to handle failure there using the Akka library. And you can see how cool and easy actors are. So thank you very much for listening. I hope you enjoyed the presentation. Any questions?
Yeah, I have. So I saw that you allocate actors based on some kind of constant hashing, right?
Mm-hmm.
And can we say that this is a best practice in world of Akka?
So actually it depends on your business case. So in here I'm just trying to give like the standard function that you could use, but you can decide how to allocate that.
And I'm wondering how can you cope with auto scalability? So I mean, can you just add new shards to your cluster, or just remove them based on the load?
Well, to be honest, I don't know how to do that, because every time I work with Akka clustering, it has been with a fixed number of clusters. I think now Lightweight is providing some mechanisms to be able to manage the Akka cluster better. I'm not sure, to be honest. But I think there are ways of adding some more nodes, but for that you will need to configure the seed nodes, which are the nodes that need to be there when you join the cluster, and then this new node will be able to join the cluster. So that one I know is done transparently, but I'm not sure whether it's very easy to do it automatically by starting this and removing things from the cluster.
Right. Great talk. Are Scala system IDs global? Does every node in the cluster know system IDs?
So, to be honest, I think that the cluster, the shard region, is going to manage the persistence ID that you've got allocated in each shard.
So they're not visible outside the shard?
So they are not visible outside the shards, but the shards function should be able to decide where to allocate them.
Okay.
So given the entity ID, if you apply the extract shard ID, then it will tell you the shards where the actor will live. In this particular case, I hard-coded the number of shards you've got, but actually this is something you can get automatically from Akka. So in case that a shard dies or something, you can adjust your function automatically.
Okay. The connection is that process IDs can be global in distributed OM, and that causes a problem for when you come to scale.
Okay. Any more questions? Thank you very much.
Thank you.